I have found after lots of years of doing kinematics, studying motion in one dimension and projectile motion, that I find it's all very simple and straightforward. If I can define the position and displacement, from the displacement I define velocity and acceleration, and then I solve various problems where the acceleration is presumed constant. And a warning for our physics is that we're no longer going to presume that the acceleration is constant. And so all of those equations that we love so dearly, x is equal to x naught plus v 0 t plus 1/2 at squared, and v is equal to v naught plus at, and indeed even v squared is equal to v naught squared plus 2a delta x. Those equations are only going to apply in situations where the acceleration is constant. We're going to do a much more sophisticated physics now. That kinematics is simply a tool to solve problems. The real issue for us is not to describe the motion that happens, although that's certainly something that we have to do. The real issue for us is to explain why motion happens, why physical systems in our universe evolve the ways that they do. And for a long time, this was not very well understood. And in fact, for a very long time, there was a great misconception. If I think about the earliest attempts to create a kind of physics, I would go all the way back historically to Aristotle, when it was believed falsely that it was the natural tendency of objects in our universe to be at rest or to come to rest. It's not a surprising result to make based on ancient observations. Just about everything that's moving will eventually stop moving. If an object is pushed along a flat surface, it'll move for a bit but eventually come to rest. And indeed, even biological organisms, animated in their lifetimes, eventually come to rest. So this notion of a natural tendency of rest was not surprising, but causes a huge problem for our understanding of the way the universe works, mostly because that idea is not true. And there are some curious arguments that sort of tip you off to the fact that that might not be true. And in Aristotle's time, an argument that would be made is that, would be made by Aristotle, is that an object will remain at rest until such time as some action is taken to change that state of rest. So here my water bottle sits on the table and it is absolutely stationary in a natural state of rest until I push on it and then it moves, and as soon as I remove the push, it stops moving. That is, the influence of my hand is the cause of the motion. And that's what I'm looking for, an explanation of the cause of motion. But then I have a question for Aristotle, and that's this. For example, if I take an arrow and I knock an arrow to a bow and I pull that arrow back, when I release the arrow, I understand that the motion of the arrow is caused by the action of the bowstring pushing on the arrow and causing the motion. But after the arrow is loosed, it's a curious thing to me, because there's no longer an action. The arrow has left the bowstring. So the proximal cause is gone, and yet the arrow continues to fly through the air. Well, Aristotle's answer to this, I think some of you may know, is that what's happening as the arrow flies through the air is that the air in front of the arrow goes around to the back of the arrow and pushes, which is, to us today, I think, pretty much an absurd statement. But one that actually solves the problem. Aristotle says that in order for there to be motion, there must be an actor that is the cause of motion. And therefore, when he sees a physical system in his universe behaving otherwise, he comes up with some sort of what he believes to be a rational explanation. It would not be difficult for us to create a situation like that and perform some experiment and find out that actually, no, that is not true. That it is not the natural tendency of objects to behave that way at all. But in Aristotle's time, because of the limitations of his ability to perform those experiments, it seemed like a perfectly rational thing. And it set human science back for quite a way, until Galileo comes along. And Galileo was able to imagine, for example, an object sliding across a flat surface, like this table here. An object slides along the flat surface, that there is an interaction between the object and the surface that removes the motion. And that if you could eliminate the action of that influence, that you might get different behavior. And so Galileo proposed the following sort of thought experiment. Imagine that I have a ramp here that just makes sort of like a parabola here. It doesn't have to be any specific functional shape. And I have a marble that I place here, and Galileo, of course, is famous for rolling marbles down ramps and making observations about the behavior, and particularly, also verifying some of our kinematic laws that we have already studied. You release the marble from this position at rest, and you allow it to roll, of course, to the bottom under the influence of gravity, which Galileo did not completely understand at the time. It turned out we'd have to wait a while for that to happen. But the marble rolls down to the bottom, and once it gets to the bottom, it then rolls up the other side. And what Galileo observed, or what he supposed, was that what he observed was that the marble would nearly come back to the original height that it was released from. But what he supposed was that if you could eliminate the interaction between the marble and the ramp itself, that in fact it would come back to the exact height from when it was released. So instead of imagining that an object is moving under the influence of gravity contrary to its desire to stay at rest, what Galileo imagined was what an object in this situation was seeking to return to its former height, which is also somewhat of an erroneous idea, but it leads to the very obvious and natural conclusion, because Galileo supposes, what if this ramp is then reclined in such a way? So we leave it the way it was here on the left, but on the right I recline it a little bit. And I release the marble, and what I discover is, once again, the marble goes to its original height that it was released from, despite the fact that to do this it must travel a greater distance in a greater amount of time, still striving for its former height, and again declining the ramp again in this apparatus, which Galileo did not actually build, although Galileo is famous for building ramps. And I had an opportunity in the Science Museum in Munich to see Galileo's actual ramps that he used, and some of the clocks that he built to do these experiments. But here I recline it again, and I find indeed it's true that the ball always strives to its former height when released. So then Galileo imagines, he makes the final observation here. Suppose that I decline the ramp and so that it is entirely horizontal, and I release the ball and it rolls along this apparatus now till, say, it's somewhere around here, and it's moving along with some velocity that I can define as v. And in the absence of any influence between the marble and the ramp, this is going to be motion with constant speed. And because of the way the ramp is shaped, the marble no longer has any opportunity to return to its former height, and therefore, Galileo presumes, this means that it will continue on forever and ever and never stop. And so by doing this, Galileo realizes the fact that it is not the natural tendency of objects to be at rest, but this is the critical thing. It is the natural tendency of objects to persevere in their motion. The natural tendency of objects is to persevere in their motion, with whatever they have to continue with that motion, unless some constraint or condition intercedes, is a part of that Galileo did not say. Galileo's statement was, it's the natural tendency of objects to continue in their motions. That was his contribution. But Galileo died in 1642, and in 1642 Isaac Newton was born. Isaac Newton, of course, gave us the very famous 3 laws of classical mechanics that we will study in great depth and then use with great utility to solve all manner of sophisticated problems. But Isaac Newton was aware of this, and we all have this famous letter from Isaac Newton to Hooke, I think, where Isaac Newton rather famously said, if I've seen further than others, it is because I've stood on the shoulders of giants. Certainly one of the giants that he was referring to was Galileo. And so I'm going to, in the next few lectures and discussions, talk about Newton's laws and how to apply them to the solution of physical problems. Right now, I want to focus on the very first law of Newton, which I think there's some confusion about among practitioners of physics and teachers of physics and students of physics. Newton's first law is often written out in textbooks with lots and lots of words that I won't write down here because it's boring to watch me write. An object at rest will remain at rest, and an object in motion will remain in motion in a straight line unless acted upon by a force. That's Newton's first law of motion. And there are many who say that Newton's first law of motion is simply a restatement of what Galileo said. This is basically a stolen law. I disagree with that, and I'll explain to you why. There was actually a famous physicist who worked along with Albert Einstein, a man by the name of Arthur Eddington. And if you have access to HBO, there's a movie called Einstein and Eddington is actually the name of the movie. And it's the story about their friendship as physicists. It's actually a very interesting story, well acted, well presented. But Eddington and Einstein worked together for quite a while. And a funny story about Eddington, he was a really, really interesting man. Einstein and Eddington worked together on the general theory of relativity, which at the time, well, it's still true today, but at the time was so mathematically complex and deep and mysterious that very, very few people understood the general theory of relativity. And Einstein and Eddington were working back and forth on it quite vigorously. And a reporter came to Eddington, was interviewing him, and said, "Sir, what do you think about the assertion that you're one of only 3 people in the world who understands the general theory of relativity?" And Eddington laughed that off and said, "No, that's just ridiculous." And the reporter said, "Surely you're being modest." And Eddington said, "No, that's not why I'm laughing. I'm trying to think of who the third person was." But Eddington was a little bit flip, and so what Eddington said was that Newton's first law, and I disagree with Eddington on this, Eddington said that Newton's first law says that an object will remain in motion in a straight line until it doesn't. That's not, according to me, that's not the case. I think that's just Eddington being funny. Because to me, Newton's first law is the definition of what is meant by force. Be very careful so far up to this point. I think, if I go back and listen to it, I didn't say force until just then. Because there are forces in our universe that we identify as the causes of motion. And those causes need very specific definitions. So for me, this is the importance of Newton's first law. That it is the natural tendency of objects to persevere in their motions. Acknowledging Galileo's idea about that nature of the motion of objects in our universe. Is the nature of objects to persevere in their motions unless acted upon by a force. I sort of invert that and say that if I do an experiment where I observe an object moving along at constant velocity, that is, the speed is constant in my experiment and it travels in the same direction the whole time, then I look at that and I'm okay with that motion because I understand it's the natural tendency to behave that way. But imagine another situation where I observe the motion of an object and that motion is altered either by the magnitude of the velocity changing, that is speeding up or slowing down, or the object turning in its trajectory through space, or both simultaneously. Then what Isaac Newton suggests that I do is to look for some natural constraint or condition that is the cause of that change in motion. Now, very, very lucky for the human race and for our physics is that those causes of alteration of motion in the universe can be codified mathematically and written as physical laws that I can use to do calculations and to make rational arguments, to discover new laws and devise new experiments so that my understanding of the universe ultimately deepens. So if I see something alter from its natural tendency, that's where I define a force. And so we define the very first force ever that influenced the motion of objects. This pen here, I've been chucking pens around all morning. If I give it a velocity, I find that that velocity changes as a function of time as it flies through the air. Not only does its direction change, but its magnitude changes. And I know that that's different than its natural tendency. So I seek for the natural constraint or condition that is the cause. And that, of course, is gravity. Now, we haven't covered it yet in our course, but we'll find that there's an equation for gravity, and I can figure out exactly how much alteration of motion I get if I'm very careful about that. And so then I describe the motion. I say, you see, it is the force of gravity as a natural constraint or condition that is the cause of the change in motion. I do a bunch of experiments and you say, yeah, I agree with you. But then you do experiments more carefully and you make measurements more carefully, and then you come back to me and you say, Charlie, it doesn't account for it. There's a little bit of extra acceleration. There's a little bit of extra acceleration accounted for by gravity. So did you calculate very carefully? Yes, we very carefully apply the law. We make the best measurements that we possibly can within the uncertainty of the measurements, our measuring instruments that we use. And we find that it's not quite right. Well, when we discover that it's not quite right, that the forces that we're aware of don't account for the motion, that's when we go looking for new forces, forces that we hadn't previously considered. And you probably know what force I'm alluding to. That as the marker flies through the air, the action of the air retards the motion of the object. That is, the very presence of the air is a constraint or condition which affects the motion of the object, and now all of a sudden I've discovered a new force. That by doing experiments and making a bunch of graphs and whatnot and some rational arguments, I can figure out mathematically what its form is and add it in. Every instance where I discover a new force of the universe, every instance, it is because I find some unaccounted for acceleration, and I account for that acceleration by doing experiments that determine that natural constraint or condition, and then I dub that a force. I can accept the existence of any forces you care to name, but they're always subject to experimental verification because it's experimental science. Physics is. It's all science. There are, so far as we know, only 4 forces in the universe, and that's kind of sketchy. It depends on how you name them. There are only 4 forces in the universe that we know, the fundamental forces of nature. They are universal gravitation, electrodynamic force, which is what we study in our classical mechanics here. For the remainder of this year, we'll spend time talking about both these aspects, the gravitational and the electrodynamic aspect. That make you wonder, in the first half of the course, do we only talk about gravity? No, we talk about a great many forces that you've already heard of. For example, friction. Now, friction we talk about generalized as its own force, particularly sliding objects across the tabletop. I find that their motion is altered from their natural tendency to persevere in their motions, and so I define, well, there's some interaction, the interaction that Galileo imagined between the object and the table, and that is the force of friction generalized. But really, isn't the force of friction a molecular interaction between them? Isn't the force of friction a molecular interaction? It is, and that is electrodynamic in nature. In fact, if I poke at the table with my finger, I find that there is a constraint prevents my finger from going through the table. Well, of course, I'm touching the table. Isn't that correct? Well, let's zoom in on that phenomenon and think about it. Think about what's going on there. I zoom in and I find, well, yeah, there I am right at the instant where my finger is touching the table. I zoom in further and find that my fingertip is composed of cells and that those cells are in contact with the table. So contact with the table is a little bit more complicated because the cells are touching the table, the fingerprints, the rises and the swirls and all those little details. But if I zoom in further, I find out that the surface of those cells are proteins and that the proteins are coming close to the table, but they don't actually touch. Physical contact is an illusion. It does not, in fact, exist at all. You never actually touch anything. Because in order to get the protons, for example, in the table, and the protons in my finger to actually come together and physically touch has a name. It's called nuclear fusion. It happens, in the core of stars, but it does not occur, it doesn't even get close, actually, on an atomic scale. It doesn't even get close when I'm touching the table. So there are forces that we'll identify for our purposes of doing our everyday sort of physics, because if we're going to tie a rope to something, it does not help us in general to imagine that the rope has fibers and that those fibers all have molecules associated with them. It's electrodynamic forces. We don't need to look that closely in nature to understand in general, more or less, how a constraint affects the motion of things. But you think about all the forces that we identify, they break down into gravity and electrodynamic force, two of the fundamental forces of nature. The other two we don't talk about in our physics because they take place inside the nucleus of the atom. They are, firstly, the strong force. You learn from your chemistry, of course, that the nuclei of atoms are composed of protons and neutrons. Don't worry about the neutrons, I get the protons. They're all together really, really, really close to each other. Well, the thing about protons is that they naturally exert a repulsive force one upon the other. So when I observe a nucleus, watch me use Newton's first law again right here. I observe a nucleus and I know that protons repel each other. And then I see all these protons together in the nucleus. They are not accelerating. They should, because there is a tremendous force that compels them to accelerate away from each other. So there must be some other constraint or condition that I have not identified that is the cause of the absence of their acceleration. That force is called the nuclear strong force. It's called strong because it is fantastically strong in order to hold the nucleus together. At some point in the history of physics, physicists started getting a sense of humor about what they name things, and so that's a strong force. So it's the strong force. Well, when we get to electrodynamics, we'll make that comparison. And then you look at a proton. I don't know if you're aware of this in general, but a proton is composed of 3 quarks. And electrons aren't composed of anything, so far as we can tell. Electrons are nice and pure, immortal, identical, live forever, it's wonderful. But a proton is composed of 3 quarks. And something's got to be holding the quarks together, because the quarks have positive charge. And so the quarks should repel each other, and a proton should blow apart. And since it doesn't blow apart, there must be some constraint or condition that is the cause. And we call that the weak interaction, because it turns out that that force is weaker than the strong force, and so they call it the weak force. So there are 3 fundamental forces of the universe, 2 of which reside purely inside the nucleus. So what I'm impressing upon you is this, that identifying forces reside solely in observing objects behaving other than their natural tendency. It's funny, it reminds me back to that thing that Feynman said, that which is not expressly forbidden is mandatory. If there's no reason why a thing shouldn't happen, then it should happen. If a thing doesn't happen, then there must be a reason that it doesn't. And then so you go looking for the reasons that are the cause. And that's the nature of Newton's first law, the law of inertia. A story that I often like to tell at this point is how it's interesting that something so simple and something so well established for hundreds and hundreds of years, for centuries we've had this. Physics students have been learning about Newton's first law. And yet 2 physicists can have an argument about it. I want to tell you about an argument that I had with a physicist at the University of Pennsylvania about the nature of Newton's first law. And I'm going to express to you 2 points of view, and I wonder which one you'll agree with. But imagine that I have an object that's moving here. I'll draw and it's moving along with constant velocity. And I look at that and I say, well, it's moving along with constant velocity, and that doesn't surprise me because it's the nature of objects to move along with constant velocity, and that makes sense. But then I add in a little bit of gravity to the experiment for the purposes of making this argument. I don't like how that arrow is pointing. For the purposes of making this argument, I'm going to have godlike powers, and I can turn gravity on and turn it off, which would be swell. But there's the object that's moving along. I turn a gravitational influence on. That is, I add a force that is the force of gravity. I'll very sensibly name it F sub g here. And so what's going to happen is this object will deflect from its otherwise rectilinear path under the influence of the constraint of gravity, causing alteration of the motion in this way, right? It becomes a projectile. We get that. And so by observing the change in the motion, that's how I define the gravity. That's how I ultimately write an equation and say this is how gravity works. The function of gravity is by observing the modification. And everybody agrees with that. But now I'll do a funny thing. And I'll imagine that this object has some little electric charge, positive charge. May add a few protons to it or take a few electrons away. And now there is an electric force, Fe, which is directed upward. And I can control that too, because of godlike powers in the experiment. I'll control that too and figure out how much magnitude of that force I'm going to have. And I dial it this way and dial it that way. And now I dial them in such a way that the influence to cause the alteration of motion of the gravity downward is exactly equal as the opposite influence of the electric force upward. You would say, maybe in a casual way, that these two forces cancel each other out. And so what I observe, if I have a blind so you can't see what I'm doing as I'm tinkering with the universe and creating these forces. I move the blind away. And then what you observe is the object moves along with constant speed. Two viewpoints. Viewpoint A. The object moves with constant velocity because the sum of all of the influences that would alter its motion is zero. Opinion number two. Viewpoint A? Okay. Now, viewpoint gamma. Viewpoint B. If I observe the object moving along at constant velocity, it is subject to no force at all. Viewpoint A. The object moves with the constant velocity because the net influence is zero. Viewpoint B. The object moves along with constant velocity because there is no force. And me and another physicist standing toe-to-toe on Locust Walk argue about Newton's first law. And there is no winner because I'm pretty sure there's no correct answer to that. What do you think? You think A, the net force is zero? There's a notion that exists in literature. I can't remember. They don't exactly call it the same thing in literature. Maybe one of you will recall. There's a thing that exists in physics and chemistry, certainly, called the preposterous fallacy. And it's the notion that objects like electrons, for example, feel something, that they have human emotions, wants, and desires, and projecting those onto objects causes you trouble in physics. I guess it's personification in literature. The preposterous fallacy is this. For example, in chemistry, you have your... That actually broke. You have your two electrodes, and the negatively charged ions want to go to the anode. They want to.
Like if you ever said that, they don't want anything.
Right, that's good. They don't want anything. They don't have any desire. So my question is, what does this particle feel? Does the particle feel pulled by two forces and they're equal and therefore it goes in a straight line and doesn't accelerate? Or does it feel nothing? Yes. Now, the problem with both of these points here is that as a physical system, you're quite complicated. Right? You're grabbed hold of in different parts. You have bones in the structure, you have muscles, and you have musculature, and the whole thing and where it goes and how the forces distribute themselves. Imagine that this is a fundamental particle. It has no parts. Right, but you experience nervous sensations according to being pulled. The particle doesn't experience any nervous. That's the metaphysical question. Do the forces exist when there is no experimental evidence to suggest that they exist? It is impossible, even in principle, for you to observe an object going along at constant speed and from that determine that there are any forces acting at all. Because the presence of acceleration is where you identify forces. In the absence of acceleration, forces don't exist. And you say, oh no, Shida, but yeah, it does, because the gravity, the gravity always exists. Gravity is very reliable. It always exists. Does it? I mean, it always has, but does it? Always? Or does it exist only in the context of acceleration? Well, I'm having fun with this idea here. There really is no correct answer. I'm not going to reveal to you that, how we actually understand it is this. We don't. All I'm doing is driving home the point that forces are defined in the context of acceleration. There are four fundamental forces of the universe that we define, but there is a more limited set of forces that we will use in our physics. So I want to run down that list of forces that exist by defining them in the context of how they can produce acceleration. So here's the list of forces. Many of you will be familiar with these forces because you may have used a list of similar utility in a previous physics class. And I'm just going to go and run through it again because I need to identify forces. Naturally, everywhere when we're doing terrestrial applications of our physics, everywhere on the surface of the Earth, there's a gravitational influence. And so any problems that we solve that are not far away from any gravitational influences, which is a rare problem for a student to be asked, it may happen, there's going to be gravitational force that is a constraint or condition that causes influence in the motion of a physical system. So I will consider that force the force of gravity, and I call that force weight. The weight of an object and the mass of an object are two completely different things. Weight and mass are not the same thing. Although it turns out to be true, as far as we can tell, that the weight of an object is exactly proportional to its mass. Here's what I mean by that. It's actually an interesting point of physics. The quantity that I know as mass, and I probably should have said this previously, but do things a little bit out of order. The quantity that we know as mass is a measure of an object's inertia. That is, it's a measure of the extent to which an object has the tendency to resist changes in its motion. There are some objects whose motion is more easily changed than others. That is, under the same influence, I get different accelerations when objects have different masses. In fact, I would like to propose an experiment that I could do in order to define when two masses are in fact equal to each other. Imagine that I have two masses, m1 and m2, and I connect them here with a rod, m1, m2 down here. I connect them with a rod, and right in the center of the rod, perhaps I tie a string to it, something like that, such that I can apply an influence. And by influence, I mean force. So I apply some force to the center of that rod. If the rod does not rotate under the influence, that is, if both objects m1 and m2 have identical accelerations under these conditions, then I will find, or I will claim, that m1 and m2 are masses that are exactly equal to each other. I know, it's exciting. Another way? Well, okay, so I can define that two masses are equal to each other. How do I identify an individual mass? There are lots of ways of measuring mass, but really there are two fundamental ways. One is gravitationally, that I measure the weight of a thing, and from the weight I determine the mass. Another way is in terms of measuring its inertia, much like this experiment, but imagine I take a mass and I put it on a spring and I allow that spring to oscillate. That is another technique that I can use that we'll we'll study in significant detail later. But that's another technique that I can use to determine the inertia of an object, is to allow it to oscillate on a spring and figure out its inertia from that. So far as we can tell in every experiment that's ever done, the gravitational mass and the inertial mass of objects are exactly equal to each other, to the precision of the experiment. So far as we can tell, they're exactly equal to each other, and the inertial mass of things is exactly proportional to the gravitational mass. So I have an equation for calculating the weight of things. I simply multiply the mass of the object, which is a measure of its inertia, by the local gravitational strength, which some of you have probably already identified, and we'll correct that a little bit later on, as the acceleration due to gravity, or lowercase g. And so the weight of an object is simply calculated by multiplying the mass of the object times however much gravity there happens to be around. If two objects have identical masses and they're at the same location, then they will have identical weights. It may seem like an obvious statement, but it's something really fundamental going on with gravity that turns out to be. So all objects near the surface of the Earth have weight, and I'll have to consider that whenever I'm solving problems, identifying the forces. The second force on my list is a very, very practical force, because at some point I'm going to be using these ideas given to me by Isaac Newton to solve problems. And in solving problems, it will turn out very often that I do not know the nature of the forces that I'm being asked to use in a problem. Right? The fundamental nature may not be known. I know that ultimately most of the forces that I'll be dealing with in my classical mechanics are electrodynamic forces. But when a man is pushing on a piano, I don't know the fundamental nature of guy pushes on a piano force. Perhaps in a godlike sort of way there's an equation for that, but there certainly isn't a practical one. And so whenever I'm solving problems, very often, as I said, even our friction force is generalized. because I don't need to know the specific details of how everything works. So guy pushing on a piano force is just a force that I include. The important thing is that I've appreciated that there exists some condition and that I include that into my analysis, because if I leave those conditions out of the analysis, my analysis naturally will be wrong in their absence. So I'm very careful about that. We love in our physics to use ropes to make things happen. Tie a rope to something and you can pull, but not push, unless the rope's sort of starchy. You can pull on an object, and the convenience of using ropes is that the influence exerted by a rope is exactly in the direction of the rope itself, and so you can make diagrams where it's very unambiguous. The direction of the force is applied, because when a man pushes on a piano, it's very difficult to see in what is the exact direction of the force. In terms of Newton's second law, we'll discuss in the next lecture, it's critically important that I know not only the magnitude of the influence, but also the direction of the influence, because we'll discuss forces in the context of forces being vectors. But anytime I encounter a rope, we describe this as tension in a rope. Tension forces and push-pull forces, whatever. I mean, why do you call it a tension? Why not call it a pull force? That's fine. The critical thing is that I don't call it twice. You don't say there's a rope attached and that rope pulls, and then also include a tension influence. You can't double count the influences, obviously, because that too, excess forces in your analysis will cause you serious problems. Whenever two objects come in contact, as I was just alluding to by touching my finger to the table and talking about the intermolecular interaction of my fingertip in the table, it's electrodynamic nature. Anytime two surfaces come in contact, there is a force of contact that we call the normal force. The normal force is the force of contact. It is called normal because it is perpendicular to the two surfaces which are in contact. When I touch the table pushes upward on me as I push downward on the table, perpendicular to the surface of the table. That's the nature of the force of contact, the normal force. And so anywhere two surfaces are in contact, there's a normal force. Well, when Guy pushes on a piano, there are surfaces in contact, but I've already accounted for that. I've already accounted for that as a push force. I don't want to double count. Mm-hmm. Yes, it does. So there's a thing, very often when we encounter normal forces, for example, a normal force is me standing here. And so here I stand, and I'm not accelerating, which is weird because I know that there's gravity. So I look for the gravity, and I account for the gravity, and now there's gravity. I should fall. Why don't I fall? There must be some other constraint or condition preventing me from falling. Well, it's the floor pushing upward on me. So how much influence must there be? Well, the answer is obvious, a sufficient amount of influence to keep me from falling. I don't know what that number would be, but a sufficient amount of influence to keep me from falling. But what if the floor is like a bad floor and it collapses and the normal force becomes insufficient? Well, that's exactly what happens. The normal force changes to a number that is less than my weight directed downward, and now I must accelerate downward. That is, in the imbalance of those forces, which is more appropriate to talk about with Newton's second law. In the imbalance, the acceleration must occur because they are no longer in equilibrium. But so I stand on the floor. If the floor breaks, it's embarrassing. It's a wooden floor, I guess. Creak, crack, snap, whatever. The physical, all those little mechanical failures inside the wood, in principle, is what reduces the normal force and allows me to fall. But it is a very complicated thing. I mean, I like that you think about it, but very often these interactions, it's why the spherical cow joke makes sense, right? I can solve the problem as long as things stay, but when the floor starts to break, the situation becomes so absurdly complicated that a Newtonian analysis might not work, and an experimental analysis might be more appropriate, like the kind of failure engineers do. Because I've come up with and people try to do this, they try to come up with a theoretical analysis of ductile failure. You take like a metal rod and you pull on it until eventually it breaks, and try to understand when does that breaking happen, which obviously is a very good engineering thing to know, strength and structure of materials, so that I can build things that last forever and ever. But it's extraordinarily difficult calculation. No, because even that, this is a little bit absurd. Answer one. It is an enormous amount of force that you will never exceed in any kind of practical thing. In order to exceed that force, you have to do something absurd. I have to punch the table so hard that the atoms in my fist fuse with the atoms in the table. That makes me more powerful than any superhero that has ever been imagined in any comic book that you have ever read. Remove from your mind any suggestion that the normal force and the weight force are related to each other. They're not. In the context of a specific physical system, there might be a relationship in context, but fundamentally there is none. The value of the normal force in principle is unrelated to the value of the weight in any way. In the context of a problem, it might be. I might write an equation that has the weight in it and also has the normal force in it, and therefore that implies a relationship. But the normal force is not caused by or related to the weight in any way. In fact, I can have a situation where the normal force acts horizontally, perpendicular to the weight, so that there is no interaction between at all. And also, if you want, I can get on an elevator where the normal force is directed upward, the weight is directed downward, the elevator accelerates upward, and therefore the normal force upward is larger than the... So there's a list. Now I'm going to develop an equation for this next force, very familiar force, and that is the force of friction. I'm going to leave it be right now. Ooh. The force of friction is the force that opposes the relative motion of surfaces when they come in contact. It's, common in our everyday lives, so we have some sense of it. But of course, in our physics, we will formalize that so we can use it to solve problems. Sixth on my list of popular forces in physics is a spring. Spring is really nothing more than a coiled bit of metal, but it turns out to be fundamentally important to our understanding of physics on all scales and all levels. Really, really critical that we get a very good hang of the spring forces, so we'll do that. So I've named all of the forces that I'm likely to encounter in a course such as ours. There are many other generalized forces that exist. In fact, if you start doing some experimentation in an exotic area of physics or engineering, you might, or even chemistry, you might discover your own force. The most recent new forces that have been discovered, within the last decade, particularly molecular interaction forces are always being found. You learn in chemistry, you've heard of the van der Waals force. That's not the only molecular interaction force that has been identified in the history of our science, and so we can encounter more and more forces. So to sum up, the point of today's discussion, was to realize that what Newton's first law does for me is to acknowledge the fact that it's the natural tendency of objects to persevere in their motion and to give me a definition of what is meant by force. When I see an object behave in a way that is different than its natural tendency, then I say that there is some natural constraint or condition as the cause of that.